All right, let's start today's lecture. We start today's lecture with an old topic, right? Project 1, we've almost done the marking. So hopefully, no, definitely we will release the final marks of Project 1 in this week, hopefully early this week. Well, I have to say that I am a little bit disappointing to see that there are more than 50 students who has got a 0 mark for their programming part in Project 1. Considering that we have released 2 test data sets, one is the toy example. Even if we don't count it as one, we did release another data sets several days before the deadline. And well, now I can tell you that this test data sets is one of the 3 test data sets that has been used in the marking of Project 1. So there's really no excuse if you can't get at least some points, right? Some points in Project 1. Many of these 50 students, the reason of 0 mark is because the incorrect implementation. So basically, we have, providing that we have given you the pseudocode and given you the script that to show how we are gonna execute your implementation. This is not what I'm expecting to see. Wow. But anyway, past is the past. Now we're facing Project 2, which, by the time that you see this video, Project 2 will be released already. So now Project 1 was 25 points of your total mark, or of your final mark of this course. And Project 2 contributes another 25 points. So if you did not do very well in Project 1, I urge you to throw more time on Project 2. And Project 1 is a little bit tricky. Especially if you want to get full mark. You need to figure out that despite the efficiency of your implementation using those RDD operations, the algorithm itself is not efficient enough. Right? The inefficiency mainly comes from when we increase the offsets. If we increase the offsets 1 at a time, then we will spend a lot of time to do the checking, and each time when we check the offset, we count the hash values to count the collisions. It involves several RDD maps, and each map means you scan the dataset once. Right? So this is where the inefficiency comes from. So from the algorithm perspective, you need to figure out that how to speed up this probing of offsets, or how to find the best offset as quickly as possible. So I'm very happy that I've gained the permission of 2 students who has both got the full mark. Not only for the for the 100 points, I mean for the regular parts, but also for the bonus part. So these two students got the first place in tie in the bonus part, and they gave me the permission to release their code and the report. So you can see what a efficient implementation would be looks like, and I will release their code and reports on, I think, on Tuesday. Yeah, on Tuesday. I mean, after I've collected all the submissions, and hopefully I will release the final mark of project 1 on that day as well. All right, so that's about project 1, and for project 2, it's not that tricky, I have to say. So basically, we have split the whole stacking process into several components, and we're not requiring you to implement all of these components. We only requires you to implement 3 components. So 3 tasks, 3 tasks there. Each was 30 points. So 90 points comes from the implementation, and 10 points from the report. So for the report, you are requiring to evaluate your model and try to improve the performance of your model. Well, I've seen a lot of questions in Piazza regarding to what should we do for the report, or how can I get the full mark for the report? What should I answer? So for the report, it's actually pretty easy. I mean, I just want to see your efforts. For example, there in the report, all the questions are open questions. There is no standard solution. But I'd rather to see your efforts than a short sentence or just the numbers. Right? I want to see your efforts, see your thoughts through the report. Right? So that's for the report. And for the tasks, these 3 tasks will be tested independently. Okay, means even you didn't do the first task, for example, but it will not affect the evaluation of your rest 2 tasks. So don't give up. I mean, even if you cannot do all the tasks, I mean, try your best. Try your best. And the 3 tasks do have different difficulties. In general, in my opinion, I think task 1 is easiest. Yeah. Task 2 and 3 maybe equal easy or equal difficult. Maybe task 3 is a little bit easier, but anyway, the gap is not very large. All right. So that's for the tasks. Just to try your best. The deadline is by the end of week 10. So this is the unit's policy. Running time threshold, yeah. Just as in project 1, we still have a running time threshold. It is very loose, of course. And it won't be a problem if you use data frames and machine learning library methods. So if you remember, we have a figure in, I think in lecture 7. Yeah, in lecture 7. Sorry, in lecture 6. So basically, data frames are much more much more efficient than RDD operations. And it is from my own experience. I mean, for RDD operations in Windows, it might be quite slow, but but for those for data frame operations and machine learning methods, the gap is much smaller between different operation systems. So the time won't be a problem. And try not to use RDD operations if actually you don't need to. And don't worry too much about the time threshold. I mean, for example, in project one, yeah, I think only 3 or 2 students actually failed because they can't reach the time threshold. And I have to say, we have set a very large time threshold for project one, so it won't be a problem for project two as well. All right, so that's for project two. Also for assignment one, we have 1 week before the deadline. So if you are not started yet, start it now. And in PIADA, I have seen a lot of questions come up every day. Well, if it is possible, I would like you to check whether this question has been asked before. I did see some duplicate questions, so it would save the time for both of us. All right. So that's pretty much for project two and assignments and projects. Yeah, we probably on Wednesday we will explain a little bit more about project two. I mean, depends on the feedbacks from you. All right. So I will collect the the questions in PIADA and try to give you the feedback in Wednesday's lecture, and it might be in the lecture of next Monday. So that's for the project, and now let's start today's new contents. So today we're gonna discuss the data streams. All right. So mining data streams, and today's lecture slides mainly comes from Dr. Cao Xin, which is the lecture in charge of this course several years ago. So thanks to Dr. Cao to share this slides with me and allow me to present it to you, because yeah, as you will see soon, I mean, this data stream is also a challenging and essential, important topic in big data management. All right. So data streams. So the firstly, it's about what is data streams, right? The definition of data streams. So basically, in many data mining situations, we don't know the entire data set in advance. This happens a lot empirically. For example, all this real-time generated data, right? For example, data from Google's search engine, or tweets, or Facebook posts. Basically, you cannot expect to have the entire data in advance, right? And stream management is important when the input rate is controlled externally. So unlike the database management system, where we can control how or when to do the updating and control the input data rate, but empirically in many situations, the input rate is controlled externally. It does not controlled by the stream management system, right? Right. Yeah. So here it's just 2 examples, and for example, the Twitter or Facebook status updates. So the input rate is controlled by who? By the user, right? By the user. So for the data management system, which you can think it as the server or in Facebook, it does not has the control, right? And in data streams, we can think of the data as infinite and non-stationary. Okay, so infinite means the data will comes over and over, and there's endless of data, right? Endless of data. And non-stationary means the distribution of the data, it changes over time. For example, you can think of like the topic of Twitter, right? The topic of the tweets in Twitter, right? You can imagine. I mean, in February this year, the hottest topic might be COVID-19, right? But in June, so in last month, the hottest topic might be Black Lives Matter. And in this year, in this month, at least in Australia, I believe the hottest topic becomes COVID-19 again, right? And so from this, you can see the distribution of the data actually changes over time, right? So these are some characteristics of data streams, and there are more, right? So traditional database management system, the data stores in finite and persistent data sets, or say immutable data sets, right? However, for data streams, the data in data streams is distributed. They may come and store in different machines or in different sources. Continuous, we will discuss this later. Unbounded, so basically you don't know the bound of the data in data streams. Rapid is the speed of the generation of the data. Time varying, so as you can see, the distribution or the characteristic of the data in data streams actually varies with time. Noisy, so you can expect dirty data or noisy data in data streams. Well, this noisy, it actually in the sense of that, for example, let's see, let's take Twitter as an example again. So if I just want to collect the tweets that is related to COVID-19, let's say. So all the other topics, all the tweets with other topics can be considered as noisy. All right. So that is, but in database systems, usually all the data in one table, they have similar characteristics, or they have similar topics, or even so. This noisy thing is much rare to see. Right. So continuous, from one perspective, it can refers to the continuous data, right? So for data streams, we have a huge volumes of continuous data, possibly infinite. So the data comes continuously. Right? Another perspective of continuous is about continuous query, which we will discuss later. And it also, the data is fast changing and requires fast real-time response. Also, the random access is expensive. We have mentioned these concepts a couple of times through this term. So basically, the random access usually happens on disks. Right? I can't say it is impossible that we store the data on the disk, but if you read from the disk, the random access is expensive. So usually for data streams, we consider the data can be read only once. That is so-called single scan algorithm. Right? So for each data, we read it only once. And we store only the summary of the data seen thus far. So this store usually means store in the memory. So the memory space is limited. That's why we can only store a part of data. But rather than a part of data, we store the summary of the data seen thus far, which should be more informative, right? So these are the characteristics of data streams, and empirically, the problem is challenging because we have a massive data streams. So the size, the size of the data is massive. Data is continuously growing faster than our ability to store or index it. For example, there are 3 billion telephone calls in US each day, 30 billion emails daily, and 1 billion messages over phone, right? And for scientific data, NASA's observation satellites generate billions of readings each per day, and IP network traffic, you can expect up to 1 billion packets per hour per router, and each ISP has many routers, or say hundreds or thousands of routers. Also, the Internet of Things, if you still remember at the beginning of this course, you've got a large number of sensors, for example, and they generate data each seconds, right? All these things can be seen as streaming data, and as you can see, the size of the data is extremely large. So basically, you can't expect you can store all of them. I mean, if you do the storing, it's a large cost, right? So you can't expect you store all of them. Then you can't expect you can index them, right? So we do the abstraction to formalize this stream model, where the input elements enter at a rapid rate at one or more input ports, or say streams. So they can think as you can think them as input sources. So we call elements of the stream tuples. So the system cannot store the entire stream axibly. Right. Then the question would be, so how do you make critical calculations about the stream using a limited amount of memory? So here, there are two critical points. One is critical calculations. One is a limited amount of memory. So for limited amount of memory, it is easier to understand. I will save it for the next two slides, which you will see a better illustration using two figures to show the difference between DBMS and data stream management systems. And for the critical calculations, in this week's lecture, you would see different operations or the functionalities for streaming model. And these are the examples of so-called critical calculations. So the lecture, this week's lecture is all about these critical calculations. How do we do them with the condition that we have a limited amount of memory? So keep these two things in mind. So as so similar to the lecture about LSH, we don't explicitly consider distributed systems like Hadoop or Spark. So we consider the problem setting in a more simple environment, but it does not mean that the techniques cannot be used in a distributed system, or it does not mean that a distributed system does not support operations for data streaming. In fact, for example, Spark. Spark has a Spark streaming, which is an extension of the Spark API that enables a scalable, high throughput and fault-tolerant stream processing for live data streams. Right. So we do have support from distributed systems. But again, back to this course, back to this topic, I mean, we will focus more on the principles of these algorithms or of these say critical calculations. All right. So the data processing in a database management system would be like you have ad hoc queries, which is the input of the processor, and the processor would obtain data from data storage. So the data storage could be a relational DBMS or NoSQL or big data processing platforms and other data processing platforms as well. So the processor will give the output. So for this part, you should be familiar with it, as it is from the previous course. But for a data stream management system, the processing model is different. It's different. So as you can see, we are expecting streaming data like this. Right? So the time, you can think now is the time 0, or say it's now, and this is the time -1, for example. So it could be 1 second ago, and so on and so forth. So all you have is previous data, but there are data coming every second. So you would expect data comes later, or say just seconds after. All right, and all this streams entering, each stream is composed of elements or tuples. We have introduced the concepts of tuples before. So for the processor, it takes the data streams as input. What it has is a limited working storage and achievable storage. And it will generate the output, which is the answer to the queries. So there are several differences between DBMS and DSMS. So we will have a quick look at them. Hopefully it will give you a better understanding of the characteristics of DSMS and also the challenge of DSMS. And then we will see some more concrete questions. All right. So for DBMS, we have a SQL query, which is the input of the query processing. We have the main memory, and the main memory has data exchange with the disk or the external memory, and the data, the query processing will finally output the result. But for the DBMS, you can think the model like we don't have the external memory. We only have the main memory here, and the data streams comes and go. You can't keep all the data in the main memory because the memory is limited. And the query is continuous. Now we see the continuous query. If you still remember, I said we will introduce it later. So continuous query. So if you still remember, for a SQL query, for example, Or you can also do the aggregation, like, okay, I want to count. Say, oh, I want to count how many rows we have in this table. Or I want to have the maximum value of this column. Right? So continuous query, the format is similar. Right? I want to know, for example, the maximum value in this data stream. But you can think of the answer to this query actually varies with the data or with time. Right? Because when data comes in, the maximum value of in this data stream changes, or at least would have the possibility to change. So that is the meaning of continuous query. Right? And well, for traditional database DBMS, we store sets of relatively static records with no predefined notion of time. Right. So the record is static and there is no predefined notion of time. But for DSMS, we support online analysis of rapidly changing data streams. Right. So the data is changed rapidly, and also this change is time related. Right. For traditional DBMS, we have it is good for applications that require persistent data storage and complex querying. Right. But for data stream, we have a real-time, continuous, and ordered sequence of items, which is too large to store entirely. Also, there is no ending, so you can't expect a persistent data storage. Right? And we have continuous queries, which is different from those complex querying. Right? So here we have this two lists, which are more comprehensive. So for DBMS, we have persistent relations. For DSMS, we have transient streams. We have online query, one-time queries here, but continuous queries in DSMS. Random access versus sequential access. So DBMS, you can so the main memory has a data exchange with the disk, but for DSMS, the data comes as a data stream, so you only have the sequential analysis. Say at time X, you visit the data I, and at time X plus 1, you can read data I plus 1. You can't do it reversely or randomly access previous data, right? For DBMS, we have unbounded disk store versus a bounded main memory in DSMS. Only current states matters versus historical data is important. No real-time services versus real-time requirements. We have mentioned this before. Relatively low update rate versus possibly multi-gigabytes arrival rate. You can expect this kind of rate under the certain circumstances. Data at any granularity in DBMS, data at fine granularity in DSMS, assuming precise data versus data imprecise. So in DBMS, data is cleaned, is very well handled. But in DSMS, you would expect a lot of noisy data, right? And well, access plan determined by query processor, physical DB design. But in DSMS, we have unpredictable or variable data arrival and characteristics. So basically, it means that it is impossible to have a access plan or have the optimal access plan because you even don't have the true characteristics of the data, right? And well, so far we have seen many differences between DBMS and DSMS. Hopefully you would have a better understanding of what we're dealing with. Personally, I would think this figure is pretty much is like the best describes the characteristics of DSMS or data streams. The difficulties, the difficulties that we're facing in DSMS. So we don't have a disk. We don't have the access to the disk. Everything is in main memory. So this is limited. The data comes and go. You can't expect to keep them, right? And the data is continuous. Data is continuous. So it is very different from a traditional DBMS. So traditional algorithms or ideas or strategies that has been used for DBMS, many of them you cannot use them in DSMS, and as you would see later. Right. So problems on data streams. These are the problems, or say the critical calculations that we're going to solve in this course. So there are several types of queries that one wants to answer on a data stream. Well, these are not all of the query types, but these are the typical types of queries on data stream. Right. So sampling data from a stream, well, you would expect to construct a random sample. So this sample is not like you just take one, that simple. A random sample. So for the sampling, you would expect that this sample is uniformly, for example, uniformly and randomly sample over the whole data on the stream, or all the data that has been processed or has been in the stream, although you cannot access them again. Right? Queries over sliding windows. We want to know the number of items of type X in the last k elements of the stream. Filtering a data stream, we only want to have those elements with property X from the stream. And counting distinct elements, we want to know the number of distinct elements, or the unique elements, in the last k elements of the stream. So all these last k elements, you don't think this k is small. I mean, if k is small, or small enough that you can fit it into the main memory, then it will not become a problem in data stream. So this k would be large, or at least larger than the main memory, means that you can only have partial of these k elements in your memory. That's why, I mean, you need special solutions for these problems. And you can even think this k is as large as the total size of the stream. So this k is quite different from common sense. Now with this problem solved, we can have this. We can support these applications. For example, mining query streams, like Google. For example, Google wants to know what queries are more frequent today than yesterday, right? Mining click streams, like Yahoo wants to know which of its page are getting an unusual number of hits in the past hour. Mining social network news feeds, like looking for trending topics on Twitter or Facebook. sensor networks. Say many sensors are feeding into a central controller. Telephone calls records, where you have data fed into customer bills as well as settlements between telephone companies. IP packets monitored at a switch, where you gather information for optimal routine. So basically, all these things requires operations or critical calculations on data streams, right? On data streams. Now let's look at a concrete example here, where we consider a IP network data. So networks are sources of massive data. The metadata per hour per IP router is gigabytes, right? And the fundamental problem of data stream analysis is that there are too much information to store or transmit. So we can only process data as it arrives. And also remember, we have a limited memory space. So basically the data comes one pass, right? And in a small space where we would need the data stream approach to handle it, right? So in this scenario, the approximate answer to many questions are okay or acceptable if there are guarantees of result quality. So it is just something like in LSH, we would accept a approximate answer as if the result quality can be guaranteed or probabilistically guaranteed. All right, so that's all for. I think that is pretty much enough for a brief introduction of the data stream. Now from now on, we're going to look at specific problems in data stream management system, and along with the solutions. All right. So the first question or problem we're going to study is the sampling from a data stream. So the motivation of sampling from a data stream is simple. Since we cannot store the entire stream, then obviously, I mean, it is at least, I mean, we can store a sample of the entire stream. So the sample of the entire stream would give us some idea about the characteristics of the data stream. For example, here, consider these are the data in the data stream, but with this sample, we would have gained the information that approximately, say, the red ball, the number of red ball is 3 times the number of yellow ball, right? And the number of green balls and blue balls are likely to be equal, which are 2 times the number of yellow balls. As you can see, the characteristics that we gained or obtained from the sample of the data stream is in general or approximately accurate to the characteristics in the original or in the whole data stream. Right. So there are 2 different problems or sample problems. One is that we sample a fixed proportion of elements in the stream. For example, 1 in 10 means we keep 10% of the elements in the stream. Right. So the problem of this fixed proportion sample is that as the stream grows, the sample also gets bigger, because we always keep 10%, for example, 10% of the stream or of the total size of the elements in the stream. So when the stream grows, the sample size will be becomes larger, right? But remember, the size of the main memory is limited. It's limited. So if we set this portion to be large, so at first, if we set it to be large, it will give us a better representation of the data stream, but the space is growing faster, and you can expect that sooner or later the main memory is not enough, right? So you cannot you cannot use this method anymore. If we set the proportion to be small or even tiny, then it can last for a long time or can handle a data stream of a large size, but it is less informative, as you can expect, because the portion is small, right? So the second problem, or the second type of the problem, is that we maintain a random sample of fixed size over a potentially infinite stream. Right? So when the stream grows, the sample size would be always the same. It's fixed. Right? So at any time t, we would like a random sample of s elements, and at any time, I mean the sample size is always s elements. Now, for all these two problems, what is the property of the sample that we want to maintain? So this is important, as we want to know what we need to do, right? So for all time steps t, each of the t elements seen so far has equal probability to be sampled. I mean, no matter we use a fixed portion sample or we have a random sample of fixed size, we always want that so each of the t elements, or all the elements in this data stream, or has been appeared in this data stream, we want them to have equal probability to be sampled. And this property needs to be maintained over time. See, it's not at this time, but at any time, we want any elements has an equal probability to be sampled. And this, in fact, makes this sampling difficult. Now let's start from sampling a fixed portion, which seems to be easier. So the problem is sampling a fixed portion, the scenario where we have some assumptions, right? So say the stream of tuples, so it is a stream of tuples. We would have a user, a query, and a time. So it is a search engine query stream. So each time you submit a query in the search engine, well, you have a time, you submit the query, and you is the user. So we have a tuple of user, query, and time. So now we want to answer questions such as how often did a user run the same query in a single day? So how often did a user here means actually any user, or any of the users. How often did a user run the same query means it has run a query multiple times, more than one times in a single day. And let's assume that we have space to store 1 out of 10 of the query stream, so 10% of the query stream. Now the naive solution would be we generate a random integer in between 9 to 10. Between 0 to 9. So there are actually 10 different integers here for each query, and we store the query if the integer is 0. Otherwise, we discard it. Means we ignore it. Now you can imagine that, okay, so in this case, we only store 10% of the queries. We only store 10% of the queries. And because each query is assigned with a random integer, then you can expect that any query would have the same probability, which is 1/10, to be sampled. All right, we may stop here and have a break, but here actually there is a flaw of this naive solution. Now you can think of it before you start to watch the video for next hour. Right. So let's have a break.